We're going to talk about mass defect and energy calculations for nuclear reactions. First of all, a lot of nuclear reactions occur with a loss of mass, and this mass gets converted into energy. And we can measure that energy using the Einstein formula, E equals mc squared. M is the mass, or mass defect in this case. C is the speed of light, c squared is the speed of light squared, and E is energy. Now, the energy is measured in joules, which is really just a combination of kilograms meters squared per second squared. And just to remind you of a formula that involves that, you got E equals, or kinetic energy, equals half mv squared, and m is kilograms, and you got meters squared per second squared. So you got meters per second squared, so that comes out of that. So that equals joules. So here's a typical example of a mass defect type problem. This is deuterium, which is an isotope of hydrogen, which has one neutron and one proton. And this is tritium, which has one proton and two neutrons. And when these are fused together, you get helium and a neutron. So these are all the masses of all these different particles, and you're given those masses, and they're in atomic mass units. Now, one atomic mass unit is equivalent to 1.6605 times 10 to the negative 27 kilograms. Now, the mass of a proton or a neutron is pretty close to one atomic mass unit. But of course, the mass of the atom includes the electrons as well, so there's lots of different stuff going on here. But 1 AMU is equal to that many kilograms. And as you can see, that's a pretty small mass, 10 to the negative 27. That's pretty tiny. That's what you'd expect for a mass of a proton or a neutron. The other thing you're given is going to be Avogadro's number, because that will allow you to convert something to moles. And then you've got the speed of light, 2.998 times 10 to the 8th meters per second. So you can imagine that when you square that number, you're going to get a pretty big number in the end. Alright, so the first thing you're going to do is you're going to calculate the mass defect. And the way we do that is we take the mass of the products, the sum of the mass of the products, minus the sum of the mass of the reactants. So just this number plus this number minus these two numbers here. And that gives us a negative value, negative 0.0207. The reason it's negative is because we've lost mass. The reactants have lost mass to form the products. And it's this mass that ends up getting converted into energy. Alright, so here's how we do the calculation. We've got mass, which is this much AMU. We convert that into kilograms using the kilogram AMU conversion. Multiply that by the speed of light squared. And notice how I include the units along the way here. And I'm going to end up with this many. And if I convert this to kilojoules, it'll be times 1 kilojoule over 1,000 joules. And this is where the other thing comes into play, where we're using the AMUs. They're being lost, and then we're left with kilograms, meters squared per second squared. Now that's joules, so that's what's cancelling with the joules down here. Alright, so once we get that, that comes out to 3.08 times 10 to the negative 15 kilojoules. Now that's just for one of these reacting with one of these to give one of these and one of these. I mean, it's a pretty small amount of energy. But we're not dealing with just the reactions of one of each of those. We're dealing with moles. And if we deal with an entire mole of these, then we can get this converted into kilojoules per mole. Now the unit on Avogadro's number is per mole. It's things per mole, but it could be really anything per mole, but kilojoules per mole is what we're going to end up with here. So we get 1.86 times 10 to the 9th kilojoules per mole. That's a pretty appreciable amount of energy from that kind of process, especially when you consider that chemical processes are going to give you energies in the order of maybe 200, 300 kilojoules per mole, not too much more than that. But nuclear processes can provide a whole lot more than chemical processes. 1.86 times 10 to the 9th is a pretty pretty substantial.